please do read up here and start your 9.4 work by reading page 503 in your book. And I'm looking forward to reading your one-sentence summary, which you should write right there. So part of our work, maybe even a big part of our work with Taylor series and other power series, is going to be deciding or making a claim or making a statement about when our series will be useful, when it actually converges toward the answer. So you're going to see 9.4 contains a collection of theorems that we can use for determining when a series converges. For what x values this series might converge. So just know that, sort of like, get yourself set here. Any power series, so remember power series has some kind of a binomial with x, right? So x minus a, this is the series centered at a, raised to the degree. So every term in this polynomial has x minus a raised to the next higher power. There are three possibilities. It could be that there's some number r, and this series will converge for every number that's r spaces left and r spaces right of a. Or the series could converge for all x. We saw that happen with some of the Taylor series from the last section. Our Taylor series for e to the x, the one for sine x, cosine x, actually converge for all x values. Or the third possibility is that the series will converge at x equals a and diverge everywhere else. So in that sense, in that case, we would say that the radius of convergence is 0 because there's only one number that it converges, and the interval doesn't go on either side of that one number. So the radius of the interval is 0. So the number r is called the radius of convergence. And if you write a statement to describe all of the x values for which the series converges, that's the interval of convergence. Notice if you could figure out the width of the interval of convergence, so the biggest x minus the smallest x, if you divided that by 2, you would get the radius. So the radius is always half of the width of the interval of convergence. Remember, we've talked about this, so it's just worth bringing back to mind. The only chance a series has to converge is if the limit as n goes toward infinity of its terms is 0. So if the terms don't get closer and closer and closer to 0, then there's no way that adding up the terms is going to approach like one single limit. So it's something to consider checking, especially if you have an inkling, if you have a guess, an instinct that tells you that the series might diverge. Always check that the limit of the terms as n goes to infinity is 0. If it's not, then the series must diverge. So another helpful test you might use, we call it the direct comparison test. And you can compare it to the integral comparison test from 8.4. If you can find, well, this only works on series that have only positive terms. So make sure you're using as a comparison a series that has only positive terms, and make sure that the series you're checking has only positive terms. If there's negative terms, you have to make another plan. We'll talk about even more tests you can use. But for now, assume your series has only positive terms, or only non-negative terms. If you can find a series that converges, and your series, every term, after maybe some starting values, but there's once you get to like a certain number of terms, your series is always smaller than the terms of the series that you know converges, then your series must also converge. Or if you know a series that diverges and you have a series whose terms are term by term bigger, then your series must also diverge. So I've got 2 examples here. One, they've been very helpful in specifying whether the series is supposed to diverge or converge. So we'll talk about what to do if nobody helps you with that part. But here, can you prove that the series of 1 over the square root of n squared plus 1 diverges? So I think about, it was helpful, you might like to write out some of the terms. So my first n is 0. 0 squared plus 1 is 1. Squared over 1 is 1. The next term is going to be 1 over 1. So square root of 2. This is going to be 1 over square root of 5. 1 over square root of, this is 0, 1, 2, 3, 10. So what I'm noticing is that these are always one more, these radicands are always one more than a perfect square. And I think about this series that I do know, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. So the square root of 2 is bigger than 1, which means, all right, so this one you have to know by heart. This is called the harmonic series, and it definitely diverges. So that we've talked about back in chapter 8. The harmonic series diverges. And notice that my terms here, these denominators are always less than these denominators. But if and the numerators are always the same. The numerator is 1 for both series every term. So if the numerator stays the same and the denominator is smaller, what happens to the value of the fraction? The value of the fraction increases. So that tells me that, except for this first term where they're equal, every term in my series is greater than every term in the harmonic series. And I know the harmonic series diverges, so I would summarize my answer. I would say, since my series, this series, has only positive terms, and I can compare it with the series 1 over n, which I know diverges, and term by term, my series has terms that are greater than or equal to the corresponding terms in the harmonic series. Therefore, my series also diverges. All right, so this next one is a good application of having remembered those Taylor's, some of those important Taylor series by heart. So think about 1 plus x over 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. Do you recognize this? Because maybe you thought I would give you the function and ask you to remember the series. Here's the series, and it helps us a lot if we can remember that this function is equal to e to the x. So my goal here, I've been told that this series converges. They've given this away. So I'm going to try to think of a series that I know converges and show that all of my terms here are less than. So term by term are less than or equal to the terms of this series. So notice what happens if I replace x with 2x in this series. X e to the 2x is 1 plus x squared over 1 plus x to the 4th over 2 factorial plus x to the 6th over 6 factorial plus dot, dot, dot. I know this converges. It converges for every value of x, because this series converges for every value of x, so I can simply make this replacement. That's one of those transformations I can perform. And tell me about this series that I've been given. The difference between the terms I just wrote out in this series for e to the 2x and the terms in this series I was given is that the denominator is squared. Well, those denominators are all positive values. Positive values greater than 1 and getting very much greater than 1. So if I square them, the denominator becomes larger, which means the fraction itself has less value. So I can say that since this function, this series I've been given, has only positive terms, and since e to the 2x, which looks like this, converges for all x, and term by term, the series I've been given is less than or equal to all the terms in the e to the 2x series. Therefore, this series, as n goes from 0 to infinity of x to the 2n over n factorial squared, also converges.